Hello and welcome. This video is going to look at higher order derivatives. We've already looked at taking the first derivative of a function, such as y prime, or we could rewrite that or denote that rather as dy dx, which is the derivative of y with respect to x. So this here is your first derivative of y with respect to x. And like I said before, eventually I'll get to the point where what we mean by this respect to x. Right now you can just think of it, that's the variable that's in your function that we're taking the derivative of respect to. We want to look at now, we can also take a second derivative, which we would denote as this y double prime, or if dy dx is representing the first derivative, then if we take the prime here, dy dx, that means we're taking the derivative of dy dx, which means this would be the second derivative. Or another notation here is we have this little d with this little 2 that says indicating the second derivative of y. And on the bottom, the 2 here is with the x. It looks like an exponent. That just means that we're both times we're taking the derivative with respect to x. So this here is the second derivative of y with respect to x both times. So basically you take the derivative and then you take the derivative again, and that gives you the second derivative. And of course we could do that a third time to find the third derivative. So we could indicate that with 3 primes here. Or if you have dy dx, since that's already the derivative of y, then we could use 2 prime marks to indicate the third derivative. Or just like we did above, we could write d3y, which means we're taking the third derivative, and that's with the third derivative of y with respect to x, again, all 3 times. So let's go ahead and look at an example here. Here we have a nice polynomial function, and if we want to take the derivative, we'll say y prime, then we would simply have 5x to the 4th minus 8x cubed plus 3x squared plus 8x minus 6. So there's the first derivative. And then if I wanted to find the second derivative, we would simply take the derivative again. So 4 times 5, we would have 20x cubed. 3 times 8, we'd have minus 24x squared. And then we would have 6x plus 8. And if we went even further, we could find the third derivative. And if we take the third derivative, we would have 60x squared minus 48x plus 6. And if we wanted to go even further, we could find the fourth derivative, which would be 120x minus 48. And we could actually take the fifth derivative, and you'll notice here, instead of writing 4 or 5 prime marks to this, put a little 4 and 5 in parentheses to indicate you're taking the fourth or fifth derivative. And the derivative here would be 120. And if we went another step for the sixth derivative, the derivative we know of a constant would simply be 0. Now, this is always going to happen if you happen to have a polynomial function. You can eventually keep taking the derivative until you get to 0. Now, really, for our purposes, we're usually just going to look at probably the second and the third derivative. We won't really go any further than the third derivative, and we'll look at some applications of that here shortly. So for an example here, if we have this function, x squared minus 3x divided by x minus 4, how can we find the second derivative? Well, the first derivative is going to require which rule? Well, you're going to realize here we have to use the quotient rule. So that means we're going to take the bottom function, multiply that by the derivative of the top, which is 2x minus 3, minus the top function multiplied by the derivative of the bottom, which is simply 1. And this is all divided by the denominator squared. Now, at this point, we've taken the first derivative, we need to find the second derivative. Well, we don't want to leave this in this form. We want to actually simplify this before we take the second derivative. So if we simplify this at the top, we could multiply this out. We'd have to FOIL. So x and 2x, we would have 2x cubed. And then we would have here negative 3x and a negative 8x would be a negative 11x. And negative 4, negative 3 would be a positive 12. And over here, the 1 simply is not going to change anything, so all we have to do here is to distribute the negative sign to get a negative x squared and a positive 3x all over the denominator squared. And in this case, because I know we're going to be taking the derivative, again, we want to actually go ahead and square the denominator. So that means we're going to have x squared minus 8x plus 16. And recall, if you have x minus 4 squared, that really means x minus 4 times x minus 4. So once you FOIL that out, you're going to get x squared minus 4x plus 16. So here you're going to get the negative 8x in the middle. And if we continue to combine our like terms, we have what? 2x cubed on top minus x squared. And then we have 11x and 3x, or a negative 11x and 3x, so that's a negative 8x. And then the plus 12 all over the denominator. Okay, so at this point, we've pretty much simplified this expression as far as we can really go at this point. So now let's take the derivative again, so we will have the second derivative. Well, once again, you're going to notice in order to take the derivative here, we're going to have to use the quotient rule once again. So here we're going to take the bottom function, x squared minus 8x plus 16 times the derivative of the top. So that would be 6x minus 2x minus 8 minus the top function multiplied by the derivative of the bottom, which is 2x minus 8. And this is all divided by the denominator x squared minus 8x plus 16 squared. And there's the second derivative. Now at this point we could multiply the top out and combine some like terms, but really for our purposes I'm going to say we're actually going to stop at this point. So if you wanted to simplify this further you could, but this here is the second derivative. So one thing to keep in mind, once you take the derivative and you get the first derivative, like we did here in blue, before we take the second derivative, you really want to simplify this as much as you can to make it easier for when you go to take the second derivative. All right, the next example we have here has a trig function involved. We have f of x equals the secant, and once again we want to find the second derivative. So first of all, we can take the derivative of secant x, and if you recall, this is one again you basically just have to memorize, or you can look up in the chart. The derivative is secant x tangent x. And there's not really a whole lot to simplify there, so we could just simply take the derivative again. And here, when we take the derivative, we're going to have to use, you guessed it, the product rule, because it's secant x times tangent x, and the product rule says we're going to take the first function multiplied by the derivative of the second. So the derivative of tangent is secant squared, and it's plus the second function multiplied by the derivative of the first, and the derivative of secant, once again, is secant tangent. And once again, there's the second derivative. And here we could do a little bit of basic simplification. For example, secant x and secant squared, we could certainly multiply that to get secant cubed x plus secant x, and then of course the tangents, we could make that tangent squared. And really that's a good place to stop, and you're probably going to notice though with your multiple choice problems on Blackboard, they tend to like to factor, so we could actually factor this. They both contain a secant, so we could factor out a secant x. So we're left with secant squared plus tangent squared x. And there's the second derivative of our secant function. So once again up here, looking at derivatives of the first, second, or third derivatives, probably the most we're going to look at. The notation, dy dx, derivative of y with respect to x, dy prime over dx. Again, dy dx is the first derivative, and then the y prime, or the prime rather, is indicating the second derivative, and then similar for dy dx is the first, and the 2 prime marks indicates the third derivative here.